Hello guys, so we continue our lectures today. You see the screen, right? So, any questions on the previous one?
No, except for the last question, is this about the TV? We didn't really get that one.
Sorry, say it again?
Who did invent the TV?
Oh, you didn't?
No.
No, we didn't.
Any ideas?
No.
Huh?
Any ideas on that?
The best idea we had was to ask you.
Come on, guys. You're young. Should have imagination. Any crazy ideas on this?
No, we didn't get it really.
You didn't get it?
The question itself.
No, we did get the question. We just didn't get any idea. Oh God.
There was a clue. There was a clue given to you. The clue is just what I spoke. Remember one quanta, one photon.
Yeah.
One photon can create the whole picture. Okay. In general, you may think about it. You may continue because it's a good thing, a good point to think. So you may continue, but I just give you another clue. Okay. This currently engineers and all this, they do not really understand. They don't really understand quantum mechanics as deep as it needed, and the scientists are not really working on invention of TV. Scientists are working on science, right? And engineers are not that deep in quantum mechanics. So that's the problem for now. And the clue to this lays exactly in this one photon picture. Because engineers right now, what they're trying to create, they're looking at this like the whole hologram, right? They can make a hologram, right? And they try to send it pixel by pixel. Understand, right? There are lots of pixels, lots and lots and lots. Holograms is much more dense than a real photograph because it contains a lots of information. So to send this amount of pixels just impossible for now, and probably it will be pretty much impossible in the close future. So they have just a bottleneck. They cannot overcome it. And the clue is that do they really need to have this whole picture and to send this whole picture by radio waves or whatever, or do they need something else? Remember, just the clue is one photon contains the whole thing. Can you imagine this? One single one. And engineers right now, they're trying to send like lots and lots and lots of signals. Okay, so think about it. Okay, we'll continue. Today we'll talk on certain things which is called middle. I will call in short middle and average. Probably you know what middle ground is, right?
What?
Middle ground.
Yeah, no.
No, but anyway, it's just if you stay here, right? So, and you want to put the border between you, like fair border, right? Somewhere in the middle, right?
Oh, median?
Medium, yeah, medium, middle. Just this is something in the middle.
No, it's called medium in English.
Oh, okay, but middle ground. It's not medium ground.
No, median. Like if you're talking about statistics, it's called median.
No, I'm not talking about statistics right now.
Ah, okay, sorry.
It's just middle ground.
Yeah.
Middle ground, something in the middle. Just if you're talking, if you want to divide something like in fair divide, like shares, you divide it. Like for if you have two of them, you put cut it in the middle, right? It would be a fair share or something like this. So you understand that there's something. What is called middle. So the idea of average, I don't know, have you heard of this or not? But
Yeah,
huh?
yeah, isn't this statistics?
It's not statistics, some part of, but it's not actually statistics. It's something close to it. So average comes close to the idea of this middle. What do you mean? What do you mean on the middle? Like if you have somebody have high score, right, and somebody have low score, right? So in the middle score, right, would be an average between both of them. Like something like this. Again, middle ground. So in the numbers, it looks like this. if you have two numbers, any two numbers, like 2 and like 4, right? What's the middle between them? What's the middle number between them?
It's a 3.
Yeah, it's easy, right? It's 3. It's right in the middle, right? But if you have not 2 and 4, but 2, for example, and 6.
2 and 6, it would be 4.
And again, somewhere here it will be 4. Easy to see it when you put it like this, right? This is 2, this is 4, right? This is 6, right? This is 2. This is 3, and this is 5, right? So this is middle ground. So how to calculate it if you have a numbers? Huh?
So if we're only using two numbers, then you would add the two numbers and then divide by 2.
Right. It's easy formula, right? So 2 plus 6 divided by 2, right? If you have many numbers.
Yes. You divide by the amount of numbers there.
Exactly. So we have first number, second number, plus number n, right? Value number n, and divide by the thing. You know this, right?
Yeah.
Okay. And by the way, it may be good to know that there's another. It's like this, from 0 to n. This is the denotation of sum. Sigma. It's called sigma. Capital letter of Greek alphabet, sigma.
Isn't that the summable numbers?
From 0 to n, this is the summarizing of all the values numbered by n.
It's like a loop in programming.
Index, yeah.
That's the index.
From 0 to n. From 0 to n. Just denotation, right? n divided by n. So this is the formula for average, right?
I get it.
So not that complex, right? Now let's go a little further. Like for example, if we have something like x's again with some numbers, right? And we have number 5, right? And here number minus 5, and here somewhere is 0. What will be the average between minus 5 and 5?
0.
0, exactly. So this is the average for minus 5 and 5. What about minus 1 and plus 1?
0.
0. What about, okay, whatever, 4 minus 4 and plus 4?
0.
So if you look at this axis, right, you see that to each number, whole number right here, up to plus infinity, right, somewhere, whatever, we can find a counterpart on this side, right?
Yeah.
So for 5 is minus 5, for any n, there is a minus n. Whatever number you find, always a counterpart on the other side. And also you can call plus infinity and minus infinity. So the whole axis is so-called balanced, right, around this. This is like total average of all these numbers. 0. Now let's think about something else. This is average. That's easy to see, right? But let's do that. Let's move our point of view from 0 to point 1. And look not from 0 point, but from point 1.
Yeah.
For example, take the number 5,
Yeah.
right? Which is counterpart if you're looking from this reference, from this
3.
reference point?
3.
No, that is not looking for the average.
Oh.
The balance.
Part of 5 relative to
We're taking
1.
5, right? And
What is
the counterpart for 5 when you're looking from the point 1.
Minus 2.
So again, it's maybe easier to calculate.
Oh, minus 4, minus 4, minus
minus 5. You have minus 5, right?
Very close.
Average should be 1, right? Average should be 1. This is average. So 5 plus what divided by 2
No, the question
should
is,
be 1.
what is the counterpart to 5 such
What's
that
counterpart?
another number to 5 such that
Another number which you put here give average 1.
Minus 3.
If you put minus 3,
I completely did not understand that.
yeah,
Good job,
right.
man.
Minus 3, right?
You get it?
Yeah,
So-
now I do. I'm like
2 divided by 2 will be 1, right? So this is totally correct, right? Minus 3. So can you, if you take another number, like for example n, right? So average, again, average for number n. So this is n divided by how many numbers? N. Oh, again, 2, right? It's a counterpart. What you should put here to have here.
But
N.
they shouldn't be. Wait, Jen.
Oh,
They're either not n on the left or on the right. You have to get rid of one of those.
oh yes, I'm sorry. Jesus Christ. It's not n, it's 1, right? We are talking about 1. I'm sorry. This is point 1. We're looking for a point 1 now. What we should put here to get the average 1?
So why don't we solve it Katya, why don't you solve it like an equation? N plus x over 2 equals 1. We're solving it.
Okay.
N plus x equals 1, right?
Yeah, so first you want to multiply by 2.
Yeah.
Make it n.
Yeah.
N plus, I know, n, stop, I know, n plus x equals 2. And then you get n equals 2 minus x.
You're solving for x, you ding dong.
Oh. Oh, yeah.
Jeez.
So x equals 2. 1 minus x.
Oh, did you solve it?
Yeah.
Tell us.
See the 1 minus x.
Hmm?
No, it's n minus 2 minus n.
That makes no sense.
What the heck? Well, x equals 2 minus n.
Alright?
Wait, no.
No.
But like n 2 minus n in brackets.
Huh?
2 minus n in brackets.
I don't care, Katya. Oh, actually, maybe.
You're correct.
Yeah.
That's correct, yes. Katya, right?
It's correct. Oh, no, that's correct. Yeah.
Oops, I said 1
2
minus
minus.
n.
So what is x, Katya?
2 minus n.
Okay, that's correct. But
So it is n minus 2, right? Divided by 2, right?
there we go.
So n is here, and on the left is n minus 2. With the minus, of course. It's all minus. Negative. So somewhere here. Okay, somewhere here is n minus 2. It is n and here, right? Here. Oh no, shift it here a little. Sorry, here. Okay, so we have some short formula, but anyway, you understand that for anything, if you shift it from point 0 to point 1, you can find this counterpart, this balance, right, to each of the numbers on the right, right? It's easy to see, it's symmetrical situation. So if you have 0 as average, you can as easy have 1 as average too. If you have infinity on the plus and minus. The same thing, if you think a little about it, you take any number here, like number A, whatever is the number A, right? And you always can took it as an average and find out the numbers and their counterparts to make this average for the whole axis, for the whole amount of numbers. So average is a very interesting thing. Just think about it. Average it depends very significantly depends on your point of view, on your frame of reference.
Of course, you don't average is just the other week.
Yeah. So just think about it, and now we'll take a little
What is better?
just
average?
other thing that we remove all these infinities and give only restricted axes, only from 5 to -5. That kind of axis, it's restricted. It's not going on the right, not going on the left. Only this interval from -5 to 5.
Okay.
Can this point 1 be an average now?
Yeah, it's still. I think it's
For all the numbers. It can be average for, like maybe for 4,
Yeah.
but can it be average for 5?
Yeah.
Yeah, for 5, because it's minus 3 for 5, right? So it can.
Yeah, it can. So when you restrict the thing, you are restricted in your averages too. Your average comes close to 0, right? They like shrinks the whole thing. So just understand that this symmetry only goes when the whole axis is here and not the restricted interval, right? When you have restricted interval, averages become grouped somewhere here too. So they are located. This is significant to understand. So what it means that if you have lots and lots and lots of numbers, right, the averages can be very free to move. You know, if you have lots and lots of numbers, right, averages can be here, here, here. You won't even notice where's the average is. But when you shrink the amount of numbers or shrink the size of the axis, right, you see that the average is going with this thing too. Okay, now we'll continue with a little thing. So you understand from here that the amount of numbers, the size of numbers, it gives you something different. If you come closer to infinity, the situation may change in very serious way. There is an interesting number which is not found, not calculated really, but for what year? I forgot what year was it. I forgot it. I think it's 1860. Was a guy, Italian scientist, whose name was Amedeo Avogadro, and he suggested some interesting point. He said that should exist the certain number which is called since Avogadro number. And this number, it is the exact number of the molecules or atoms in a certain part of matter. So how he comes to this idea was in 1860. Actually he come to only to idea that it should be a certain number, right? But the real number was calculated only later, after his death. I think 4 years after his death. So like 30 years later after that. So, but he suggested an idea of this, and since then it was called Avogadro number. This number, as calculated, is 6, 10 to 23 like molecules or atoms.
Like what's this number about?
Yes,
Oh, yeah.
but where this number is? What's this number? In what amount of matter this number of molecules is? It's calculated very interesting. There's a certain thing which is called atom or molecule weight. Atom weight.
Wait?
Like weight. How atom weight, right? How much
Atomic weight.
Atomic weight. Atomic or atom weight, whatever. It's a weight of atom. It can be measured, but in the beginning it was this weight was considered in just numbers. It's just numbers of protons and neutrons. They're called baryons, all of them, in molecule or atom. How many? So for example, in hydrogen, there are only one proton, and there's an electron which is surrounds it, flying around this nucleus.
Neutron too?
Huh? No, there's no nucleus. No, there's another isotope of, it's called deuterium, which contains a neutron too. But for hydrogen is only one proton, right? For helium, the second one, there are two protons and two neutrons. So and they say that atomic weight for hydrogen is 1. Just the number of the protons, just 1. And for helium is 4, because there are 4.
This is the number. This is the number that's displayed in what's it called?
Periodic table. But it's not the position in periodic table, because just wait. In periodic table, this is number first. This is number second. Oh, sorry. This is, yes, number 2. This first, this second. But this is not a position. This is just a weight. Okay. What's the question?
What about the electrons for helium? Doesn't it have any?
Yes. I'm sorry. Just this is a nucleus, right? And there are 2 electrons. 2 electrons.
They don't electrons. They don't weigh much. Is that why we don't count them for the weight?
Yes. Electrons are about 2,000 times lighter than proton. Electron is 2,000 times lighter than proton or neutron. Proton and neutron are almost the same weight, so they are counted like equally. So here is for hydrogen is 1, for helium is 4. So, and this is called atomic weight. So its atomic weight is measured in numbers, just numbers of baryons, like or protons or neutrons, whatever. And electrons, they do not count, but electrons actually, the number of electrons is exactly the position in periodic table. Number of electrons is number of position of in periodic table. If you saw it, I think you saw it, right?
Yeah.
So the position is the number of position. It is exactly the number of electrons, because electrons actually they are important for all the features that we have around. Believe it or not, but most, like 99.99, what we actually touching and feeling and everything around, all our energies, everything is connected with electrons only. And those protons and neutrons mostly they are connected with the weight. Actually, they are very, very important, but not important in our lives. In our lives, we usually touch with electrons, the hardness of material, all radio waves and everything, all connected with electromagnetic power and the electrons and everything like this. So this Avogadro number, it says that amount of molecules, right, are inside the amount of matter which is equivalent to the atomic weight on molecule weight. It is called gram mole.
Oh yeah, that's it.
I don't understand this personally.
Okay, gram mole is amount of matter in grams, because it's called gram, right? Gram mole. Amount of matter that exactly equal to the molecular weight or atomic weight of the some element.
Hold on. What is the Avogadro number? What is it?
Avogadro number, this is exactly amount It is amount of molecules or atoms, right? In this amount of matter, in gram mole.
In 1 gram mole?
1 gram mole consists of 6 by 10 to 20 to 23 molecules. Always.
Okay. And what is the weight of the gram mole then? 1 gram?
No, gram mole weight is amount exactly equivalent to the atomic weight or molecular weight. Like for hydrogen, gram mole is 1 gram. For hydrogen. For helium, it's 4 grams. Just try to get the idea, right? You have, for example, you have 1 gram of hydrogen. 1 gram of hydrogen. It consists exactly of 6 to 10 to 23 molecules. Not molecules, like atoms, right? Of this. Now we have helium. It is 4 grams. But the atomic weight is 4 times bigger than hydrogen, right? And it's again the same amount of molecules, because you get 4 times more for the gram mole, 4 times more. You get this number, 4. And you get the same amount of molecules, because each molecule is 4 times bigger.
Dada, I have a question.
Yes?
Is the Avogadro number
Yes.
so big because if they multiply by that number, they convert it into grams?
Yes, you may get this number and find out. Actually, it's one of your exercise. You find out from having this number. You can find out how much weight is of the atom of the hydrogen. Because you know that in 1 gram of hydrogen, it consists exactly of 6 to 10 to 23 molecules, right, or atoms. So you can calculate the atom weight, the real, in grams. And you think about it, how it goes. Like, okay, so this is like for hydrogen. Like for example, there is another element which is called oxygen, right?
Avogadro number.
Oxygen. Yes, O. Called O.
We'll give questions later.
Oxygen. And oxygen atomic weight is 16.
Steam. Yeah.
16.
It's not fair.
And position in the periodic table is 8. So 8 means that it has 8 electrons and 8 protons, because number of protons, they are pluses and electrons are minuses.
Yeah, Dada.
They equal.
Dada.
Yes?
Dada.
Yeah.
If the number of protons isn't equal to the number of electrons in an atom, then the atom is unstable.
Yes.
Except hydrogen?
It is called neutral atom. Neutral.
Except for hydrogen, obviously.
No. The same thing.
But hydrogen doesn't have any neutrons.
No, Papa. Because
Protons, not neutrons. Protons.
Papa, neutrons, you don't really need them.
Neutron doesn't have electrical charge. We're not talking too much about electricity, but anyway, just protons and electrons are in balance, the same amount. The only thing that proton is 2000 times heavier than electron, right? So the weight of the atom is mostly protons and neutrons. But electrons are light. So for oxygen is like the weight number, the atomic weight is 16. And so gram mole will be 16 grams. And electrons are 8 electrons. So think about this and remember this number. It's a very important number. Just remember this.
Why would it be 16 if oxygen is typically O2? Shouldn't it be 32?
No, it's atom.
Wouldn't they? Okay, fine.
And O2, this is a molecule. There are 2 oxygen atoms in the molecule O2. O2 is, yes, you're correct, O2 is the most spread in our atmosphere. Sometimes there are also O3, it's called ozone. Again, it's oxygen, but the molecule is different, right, a little. There are three atoms of oxygen. Here is 2. But for the periodic table, we have only atoms, not molecules. But interesting enough that this works for molecules too. That's why it's called molecule and whatever. Because if you have, like for example, you have O16, right? But if you count for O2, How much would be gram mole for this molecule or two? What do you think?
32 grams.
32, right? 32. But still will be the same amount of molecules. If you think about it, it's just the same. This number does not change. And that's why it's interesting. So if you know periodic table, you know how much, you know this number, you can calculate the weight of any atom of any molecule that you
And
want to.
this works because protons and neutrons
Are the same.
a certain number of grams.
Right. And almost equal. Actually, they are considered the same. They consider the same same particle in different states. Okay.
What does the Avogadro number calculate? Like, I mean, not necessarily. Sorry, I mean, like.
Go ahead, ask the question.
But what does it? What does it calculate? I mean, I know it's with molecules, but molecules.
No, they didn't calculate it. It's experimental data. They performed an experiments, pretty precise ones, and they found out how many molecules are in this in particular gram mole. Okay, so this is experiment. So this was calculated like 30 years later after Avogadro suggested that there should be set that kind of number. Now you understand that with such big amount of particles, right? That our body consists of whatever, on any object consists, like 1 gram, right? Consists 1 gram of water. It's exactly gram. It's not exact, not gram mole. For water, it is. Yeah, let's try. Yeah, no, this is for you for your question. So I would not talk about water, but anyway. So it's this is a big, really big amount. That's what we have to understand. Now, why we're talking today? I forgot to get my my wristwatch. Why are we talking about averages? Because averages, they place a lot of interesting things in physics. Like, for example, we were talking before that actually the particle, each quantum, right? Each quantum is moving back and forth. So if you have like coordinates like x or maybe y and time coordinate, right? So like each electron or proton or neutron, they move like this. If you have this speed of light, these lights, they show speed of light, so each particle goes like this in zigzag motion, called zigzag, back and forth. And each move, right or left, it makes with the speed of light. But if we look at average, it goes around this axis of t. So it's around here, right? In x. Doesn't go too far. It looks like. Or an average is 0 here for the coordinate x or y coordinate. The average is 0. So it moves like this. This comes from quantum physics. So each particle goes like this. But for us, if we look like from our perspective, it looks like it's stays almost on the t-axis. So it doesn't move any far. In actual reality, it can move very far. It can move like this. With the speed of light. And it returns back, but it can move very far.
Is it only on the x-axis or y as well?
Yes, y as well. Actually, it has rotation, so we won't talk about it like any axis, even z. If you add the z somewhere here, right? Three dimensions, right? It goes to all directions. So what is happening here? just to understand, for you to understand a little more, I would picture it a little here, right? Remember what your exercise about the globe, right? And the wave, which is reflecting from the poles, right? Remember? So you have the globe, and you have here like North Pole, right? And these are meridians. And somewhere there is like a South Pole, right? And we have waves, which goes like this. Then they reflects here, goes back. Remember that? And we talked before about the quanta as a time loop. So it's like 0 and 1 goes here and then back. So this picture actually, it is a two-dimensional analog of one-dimensional time loop. This is two-dimensional picture. They are the same. They goes back and then reflected back and forth. So it goes here and then reflected back. So you may put here like north and south.
Can I ask you a question here?
Yeah, sure.
You're talking about reflection, but there is no reflection on the ball.
It is. Remember that reflection from the open side in the tube. So yeah. It looks like that is the free. The way is free. There's no obstacle, right? But still there is reflection. And here it is the same thing. It's like focusing, like a lens focusing, because of the curvature of the space.
No, but what I'm saying, on the ball, if there is a wave going from north to south, there is really no reflection on the south. It just passes through.
It passes through. That's what I mean. That it looks like reflection.
Oh, okay.
I mean, reflection. You see, the reflection. Actually, it is like the same. You go and then goes back. It looks like it's reflected, but actually it passes through. The same thing for time loop. It goes here and it passes through and goes back, right? If you can picture it like this, from N to S, right? Like, and then it goes here, reflects and goes back. But this is just another picture for this.
Okay.
So it goes here and there. And this is the exact, this is for one dimension, this is for two dimensions. In our space-time, we have 3 dimensions of space, right? So we have waves, it looks like waves goes like from here, spherical waves, and goes up, and it goes to actually infinity, because this is the position of our particle, like proton, right? And it goes to another pole. Here it located is here, and it goes to another pole. And this pole is actually very far, or maybe even in infinity. This is the axis, right? Axis of Earth, not like Earth, like this globe. But actually we have spherical waves. This goes from this point. We look here, we have a proton, right? We release it, and immediately what it does, the wave of this proton goes out, and it reaches the infinity actually. Or it reaches the boundaries of our universe, right? This is our universe. And interesting enough, that according to relativity, the time for the proton itself, it is called proper time. So proton proper time. So the time for the proton, which released in this point, right? It doesn't take any time to reach infinity. 0 time. Proper time, tau equals 0.
Sorry, what is proper time?
Proper time is the time that actually the proton feels by itself, or neutron, or electron, any quanta.
That's because of relativity.
Yes, because of relativity. It goes with the speed of light, remember? It goes back and forth. So it goes here, then reflected from here back, but it takes 0 time for it. 0. But for us, for the proton to reach the other boundary of universe, it takes 13.5 billion years, remember? That's the time that that the light can reach the other boundary of the universe, 13.5 billion years. So this is relativity to its extreme. It's extreme relativity, example of extreme relativity. And each quanta does that. Each quanta does that. So that's why that's so weird. That's why the quantum mechanics is so weird, because of this times, the relativity of times, the relativity goes to extreme point. And now we have to understand what is going on. Okay, if each quanta is traveling like this back and forth, and its own times, it's everywhere, right? So it goes to infinity and back for zero time, or something close to zero time. It's actually, because that may be not infinity, but maybe some big distance, like 13 billion years, light years, right? The distance is light years, the time is the years. So it's for proton, it's its proper time, right? It's time for proton and neutron. And for us, it's a lots of years. So what's actually happening here? What do we have? And what we see around? Why we see around some objects that are not diffuse, not clouds, but some objects, some points, some stones, bricks, whatever, buildings? Because of the averages. Average. They're traveling back and forth, but together with the amounts like 10 to 20 to the power of 23 in each gram mole, right? In each gram mole, all these average, all these things, they collect to each other, summarize. Remember how we calculate the average, right? We summarize the whole thing, right, and then divide onto this amount. Amount is 10 to 23. So what we're doing here, we're taking, for example, any feature like position, like x, right? X, position of any proton, x1 plus x2 plus 2x to Avogadro number and divided by Avogadro number. This is on 10 to 23, right? And this is average. And this is average position of x. And we have it sum here. When we divide all these big numbers, we see something is positioned somewhere here. Maybe with some differences, but it's still somewhere here. Like me, I'm standing here, right? You are sitting there in Canada, right? So that's how this averages, that's how they works in physics. Now, any questions on this? I should be lots of but a little more about averages.
Okay, I'll explain it.
Remember, our universe is expanding, right? It has the radius like about 13.5 billion light years, right? And it's expanding. So we will take some part of this universe and we, like this picture, like a balloon, like a rubber balloon, right? A rubber balloon. But this is 3D sphere, not 2D. Okay.
If it's expanding like a balloon, then at some point won't it pop?
Say it again.
If the universe is going like a balloon, then sometimes won't it pop?
Can somebody tell me?
Open
Oh, yeah. Probably not, but who knows? But
he was not joking.
yes, I understand. But who knows? Nobody knows that. There's no answer to this. But if it wouldn't, как это лопнет будет по-английски?
Burst.
Oh, if it wouldn't explode, wouldn't burst, right? So there is a term that it may stop expanding and start collapsing. And there's a big oh, Jesus, What is big? Как это большой взрыв-то будет? Big.
Big Bang.
Big Bang. There's Big Bang right on one side. Actually, here is Big Bang. It's a North Pole, right? And here is the Big Crunch on the South Pole. So it goes, then started collapsing, and then comes to the Big Crunch on the other side of the universe. So there is, it may be, and may be experimentally actually defined. Right now, it looks like that it will expand forever, but nobody knows. Would it erupt or not? Nobody knows that. So, but anyway, so what we have here, the part of this sphere, right? But remember, it's not 2D sphere. We pictured this as 2D surface, two-dimensional surface, but actually this surface is 3D. 3D. So this is stretching. The whole this piece, right? What we take, this piece is stretching in all directions. So if we're sitting here, like Earth is here, right? And the other, like galaxies are around, and this is our galaxy, where Earth is, right? So when the space-time is stretching all directions, what will happen with these dots? Galaxies.
Yeah.
They will go apart from us, right? Just interesting point that they all are running from us, all of them. So it looks like that we are in the center. Like remember this average zero, right? Plus infinity and minus infinity. Here our point zero. And it looks like all of them are around us. We're in the center, and not only in the center, they're running out from us. But if we move here, like to other galaxy, like Andromeda galaxy, right? Here. And look from here, what we'll see? We see that, again, the same thing, because not they are running, but the space is stretching. So we see that Andromeda is again is a reference point 0, and all the galaxies are running out from Andromeda now. So there's no center of the universe. Any dot on this expanding sphere is equal to any other dot, or you may call it as an average or whatever, and everything is running out. And this is called expansion of the universe. This is actually experimental result. Probably you heard about this, right? And even more interesting that if you go further from this point, like to other point, right? The further is the galaxy, the more fast is running out from us, because it's more distant from us, and the whole thing is expanding. If you think about it, you'll see that the speed of this movement is higher than the speed of movement here.
Oh no, it's all the way around. When it's farther away,
Yes, it's further away because the whole thing is stretching, right? So when this part is stretched once, like 1 light year, this will stretch for 10 or for how many light years to there. So, like for example, to Andromeda galaxy is like 1.5 million light years. So if you stretch like for one, not for 1,000, for example, light years, right? So how many thousands are in 1.4 million? It's 1,500, right? So you understand now why the galaxies are running out, because of this expansion. And this is the average, and the average is relative again, relative. The other example of averages, pretty interesting one too. Imagine that you are counting balls in the box. You have a box, right? And there are lots of balls here. And you want to count them, right? So usually what you do? You take a ball out and put it somewhere here, right? And then how you count. But imagine you cannot do that. You just cannot do. And you have to put the ball back. And you try to count how many balls there. Would you be able to count? What do you think?
Yeah.
Huh? Yeah, it's very difficult. At least it's a very difficult task. But interesting enough, we have exactly that situation in physics, because all the balls or quanta, right, are identical. This is the law, and we cannot distinguish one from another. And when we're trying to count them, we come to interesting situation. We are getting certain numbers, because when we count, right? We're still counting. Okay, one man come and count balls, another count balls, another many attempts. So if you make many counts, you can calculate an average of all counts. And the average can be closer to the reality, but still not reality, right? You don't know. And that's exactly what situation we have in physics. The number of all quanta is not known, but the average, yes, it is calculated, is about 10 to 80, right? In the whole seen universe, 10 to the power of 80. So, but it's still average. And also, if you think a little more about like what we call coordinates, right, in our universe, that we measure distances and everything. We measure distances when we are based on certain matter, one quanta, another quanta, third quanta, whatever. If we don't have matter, we cannot measure anything. There's empty space, nothing else. So we only measure when we have some references, right? So we have to count these quanta somehow. We have to work with them, and we're doing them actually. We're doing exactly that. But all these things are very, very, very much average. And we are talking about averages, or if we talk about one single quanta, so average goes to probability. Probability for single. So it's something like this, that we have just one thing here, one ball, but we keep counting it. What we have? We have different numbers still, because we're taking it and thinking that another ball, another. So it gives you very, very average numbers, and because the ball is still one, we're talking about probabilities, one chance of and whatever. That kind of things. Just think about try to remember what we talk about probabilities. And there's a law actually in physics actually that if you have identical particles, the probabilities counted for many identical, like n identical particles, actually are calculated the same way if you have just one, but it can be in n positions in space. So one particle, because they're all identical, one particle is enough to calculate everything. It resembles this situation. Remember about this hologram television? One photon contains the whole information. So this is all like connections with all these. Connects one with another. Any questions on this, guys? No. Okay, so I have questions now. Are you ready?
Wait, not yet. Over.
Okay.
Yeah.
So this was like the last like general lecture on, for you to understand how modern physics come to understanding what is going around us, right? So it comes like from waves and something like averages, some waves that are going in a very weird way. They are spreading to the boundaries of our universe and returning back, reflecting there, and all that sort of things are like boiling in our universe. And then we see what we have around these desks, like, you know, displays, people, planets, galaxies, and everything. It happens like in kaleidoscope. You've seen kaleidoscope, right?
Yeah.
Kaleidoscope, right?
Yes.
Kaleidoscope, how it works? It has actually three mirrors that positions like this. You look from here, this is you, into these mirrors. And there are some pieces of colored glass here. So if you rotate this mirror, there are lots of reflections from all these mirrors, and it gives you these beautiful pictures that you have with the certain patterns and everything. This is called fractal picture. We talk about it in mathematics, right? A little. Self-similar pictures. So we get these pictures. But reflections, just remember that our time loops, they're the same as reflection. You return, each quantum returns to itself and see itself from back. So it reflects somewhere in the universe. It reflects and returns back. So quanta like sees each other, not each other, but itself. This is a reflection, and there are many reflections of this, which actually creates the whole world. But not the light reflections. They're reflections like in matter. They are real ones. So now you're ready for the questions, right? Okay, the first is calculate how many molecules approximately is in your own body, each of you. So you know your weight, calculate how many molecules contains your body. Approximately. You cannot calculate them exactly, right? But approximately. So consider that our bodies are mostly water. So it's like 80% water. And the water has the formula H2O. So 2 of hydrogen and 1 oxygen. And you know all the data you can take from the periodic table, right? So calculate how many molecules in average, like approximately, is in your body. Also calculate how many protons, neutrons, and electrons have your body. Get these numbers for yourself, each of you. So your dad will show you. You'll find it out, or yourself, and you calculate. Okay, how many electrons contains your body? How many protons? How many neutrons? Remember that there are 2 elements, right? Two of hydrogen and 1 of oxygen. Second.
Hold on.
Oh, you didn't? Okay.
No, in practice here, Avogadro number, comma, a gram mole.
So how many molecules, and also how many protons, neutrons, and electrons separately.
What? This is good enough. This is sort of like a keywords to trigger memory.
Yeah, I did that already.
Okay, the second is for your imagination and like invention, right? Imagine that you got, like in your hands, you got a material mirror. So the mirror that actually can materialistically mirror anything you have, so duplicate, right? So you put something like yourself, and mirror gives you another you, and whatever. So invent some practical uses of such a mirror, as much as possible.
Oh, did you say duplicator?
So something we can use it for?
Yes. These are reflections, right? So this is something like material reflector, material mirror, that reflects anything you put there. It reflects and gives you another point. Whatever. So imagine what you can do. Maybe you can combine these mirrors, maybe kaleidoscope of that mirrors, okay? So what can you create? Just think about it. And in there, okay?
And then copy them, and then there's a chance to
That's a good idea, but yeah, it's a good idea. Those things you can create yourself, and then you have a left hand at the portal.
Okay, guys, after that, okay? Just ready for the third?
Yeah.
Huh?
Yup.
Ready now? Guys.
Yeah, right.
Okay. Suggest and maybe derive the formula, right? How to calculate average for vectors. Remember how you work with vectors. Vectors, you can calculate average for vectors too. So, like for example, for velocities, forces.
You meant like average speed or?
Yes, yes, but the speed now is a vector, right? Not the number, the vector. How you work with this, right? And for you to understand how it works, like try to calculate center of mass for some simple objects. Center of mass. Antosha, you should know what is this.
Yeah.
Yeah, we're like simple graphic.
So
Yeah.
center of mass for simple objects. Or maybe more complex. You may think about it. Okay guys, that's it.
Teacher, the next one.
Yes?
Next year I can get a job.
Pardon me?
Next year I can get a job.
Say it again.
Next year I can get a job. Uh-huh.
Antosha, can you tell me? What is he talking about?
Катя говорит, что в следующем году она хочет пойти работать.
Really? Okay, this is should be out of recording, okay? So I see you next time. Okay guys, and we can still talk a little, okay?